Okay, so here is my attempt at homework 1. Hopefully this video won't be very long. So there's problem 1. We have a trolley at the Hugh Hart machine shop, and it rides on this overhead I-beam. And the force at 1, let's see, as I'm writing this down, I'm going to write these down onto my sheet. So I'll bring this over to the side here, and I will read it to myself as I'm writing it down, and hopefully this thing will focus. I'll put up my name at the top. So let's see, in the center here, I'll say that this is Spring 21, and here's the class, ES110, and I'll say what this is. This is homework 1, and I'll put my name, Dr. Deal, right there at the top. And then this is going to be problem 1. And I'll make a brief sketch of the thing, right? Doesn't need to be a perfect sketch. I'll make that a little neat here. And okay, so that's what my trolley looks like. And here's the breakout line right there. And we're going to have a force that goes approximately down that way. And here's horizontal. And this is going to be theta 1 right there. And then this is F1. And the other one here is provided here is something like that right there, F2, and here is theta 2, right? And so over here, I'm going to say a given F1, and I'll write it as a vector, is 360 pounds. And actually, I'm not going to give it as a vector because I prefer to have my angles to be through with respect to horizontal, and this one is not going to be. So I will just put these as magnitudes and say theta 1 is going to be 15 degrees. And then F2 is given to us to be, okay, no, we don't know F2. It's one of the things we have to try to find. So F2, no, I'm going to keep reading down F2, dummy. Say theta 2 was given to us, and that's going to be 25 degrees. And we want to find let's see, the resultant of the force. Let's see, it's completely vertical. So we want to find the resultant and F2 right there. And we want to do it with graphically and use parallelograms. I'm going to spell parallelogram wrong, aren't I? Parallelogram. B, graphically, with triangles. Triangles. I don't know if this is the greatest idea I've ever had. I see my eraser's gone. Triangles. Greatest idea was to do these. And here, LOS and LOC, right? Okay, focus there, focus. Was it the greatest idea to do these homework problems this way? I don't know. All right, so what I'm going to do for parallelogram, what I'm going to do is I'm going to use, which way? I think I am going to use, let's go millimeters right here. Okay, once again, so 360 would be like 36 millimeters. Maybe that's the easiest way to go. And I am going to go ahead on here and guess I'll go this direction down here. So my 15 degrees, and so I'm starting right there, something like that. And here's 15 degrees right over here. Right, so I need to mark where I'm starting from. Right to there to there. There's 15. There you go. There's 15 degrees, and we know that that is going to be 36, which doesn't seem like I'm using a lot right here. See, but see, I think this. If I use the inches right there, I think that's going to be too large on my page. I could take a scale of like 2 or something like that, but I think I'll go ahead this way. 36 is approximately right there. Okay, so there is my 36 right there. And so this is going to be F1. And then here's with the vertical, and I guess I took it, I should have taken it right onto a spot, but I took it right there, right? And let me take from here over to this side, and that was going to be at 25 degrees, so that's going to be like right there. So, right? Just to make sure that we can actually do this problem here. So we're going to go straight down, right? So the resultant is going to be vertical right there. So one of the things that we do know when in the given is that, and I should have written this out here, is that R is vertical. Is AL or LE? I think it's AL, vertical, yeah. All right, so in order for this to happen right here, right, these two things to be able to take place right in here, is that this needs to come down over to here. Wow, is that true? So for a parallelogram, for this to work out right here, and I guess I'm going to have to use extra pages right here. For this to work out for a parallelogram, the method, what I'm going to have to do is I'm going to take this, and it needs to have come like right over to there, right? Right? And then this needs to come to like right there, right here. So this would be the vector here, F2, and then this right here would be the resultant. The resultant between these two would be that. So for my estimation here, I'm going to say that F2 is approximately equal to, and it looks like it's just a little bit less than 70, or no, I should say 700, right? Yeah, because remember that this was 360, but we used 36 right here, so this is going to be like 68 millimeters, so 680 pounds, and the angle is going to be the complement of 25 degrees, right? So it's going to be coming down from that from horizontal, and let's see. So what the complement of 25 is 65 degrees, right? Right. And then the resultant here is going to be straight up and down, and And that looks like it's going to be something like 73, or we could say that's 730. And I want to approximately 730 pounds, and it's straight down. Okay. Well, let's not be stingy with paper, because for the triangular method, and we'll rewrite all these things out at the end. Let's go to another sheet right here, right? So another sheet of paper, 2, and we want to write all the other things down here. So this is S21, ES110, and my name, Dr. Deal. And this is homework 1. And so this is 1 continued. And now I want to do that same problem, and I had to use more paper because of how big I made the thing, right? And how long is this video? I gotta know. So we're at the 11-minute mark, right? So this is how long it's taking me to do my homework. Okay. So let's see, for triangles, once again, and I'm being extra careful here for my graphical method here. I'll take this point right here for my 15 degrees. Yeah, okay. That point, and I should be doing it down here, right? Okay. See, solving the thing live could show you how long it takes me to do the things. And maybe that will make some people aggravated. So, you know how long it took him to do the homework? I'm like, well, I'm not the smartest tool in the shed, so I expect more out of you. So let's go ahead and use that same scale. Right here, and that's going to be 36. So that's right around there. 36, and that right there is going to be our F1. Now, what's going to happen to this is now we are going to take, and we're going to go, I'm going to say that F1 plus, or I'm going to say that R is going to be F1 plus F2, right? That's going to be the equation that we're writing the thing for, and we know that F2 is now going to be, let's say, here's the vertical right here. From the problem, it goes 25 degrees right here. So right here is going to be 25 degrees. Right to there, and 25 degrees is like right here. So it's going to come down along that line. But we also know that the resultant is going to be, and I didn't mean to make that mark, but I almost got to the right spot on accident somehow. But like right in there, I'm going to go to the vertical, right there. Okay, so right here is our vector for our F2. Let's make those here. And then this one, so this right here is going to be the result, right? The resultant is going to be downwards. It's going to be R right in there, okay? Because that right there, this was our 25 degrees, and right in here was our 15 degrees. Up in there. So I'm going to say graphically F2 is approximately, did it again, according to this, oh, that looks like it's just at 70. In fact, it's kind of hard to say. I'm going to say that it's at 70, but it's 700 pounds, right? And in terms, once again, I think this is the same thing right here. It's this 65 degrees that's happening here. And then our resultant, it appears to be something like 72 703 maybe, or 730. So resultant is approximately 730 pounds, and that's just going to be straight down. Right, so that was part B. Now for part C, we want to try to use actually trigonometry right here. So what we could say is what we have, well, in terms of angles right here, we know that this angle right here has to be 75 degrees. And we could also say that for right here, we could break this angle apart and say that this guy right here has to be our 65 degrees, right? And this has to be 15 degrees right in there. So we have a couple of the, we have several of the angles right here. So we have the interior angle. Well, this is 75, and then this one is going to be 80 degrees. Is that true? Is 15 plus 65, 80? Yeah, it's going to be 80 degrees. So we know this is 80 degrees, and we know this is 75 degrees, and we know the length of the sine. So we could use law of sines. Law of sines down below right here. And what we could do is we could find F2 right there, divide it, and that's good. F2 is going to be opposite of 75 right here. Oh, and by the way, okay, I should also have mentioned, this is 80 and 75, so let's call this, I like to use beta. So that beta is going to be 180 degrees minus 80 degrees minus 75 degrees, right? So beta, I can't do that in my head. 180, 75 minus 80 minus 25 degrees. I could have done that in my head, actually. 180 minus 80 is 100 minus 75 degrees. Yes, duh. All right, so anyway, the opposite of, that's, okay, so this is the, okay, I just drew this. F2 is opposite of 75, so that's the sine of 75. And that's going to be equal to, we know F1, and F1 was given as 360, so we want to divide that by the sine of the opposite angle of that, which is the beta, 25, right? So I can find F2 by saying that the 360 right here, and take the sine of 25, I'll swap that, to 25, take the sine of it, and divide that, and then multiply it by the sine of 75. Boom. And, well, we get a larger number than I expect. Let me do that again. 360, let's see, I'm doing that again right there. 360, 25 sine, divided by, and then take the sine of 75 and multiply. And I get 822. Wow. That's much bigger than I expected from what I had done graphically. I'm a little concerned by that. We have to double check some things by there. I got 700 here at 822. What about my other one here? Let me take a R divided by the sine of 80. And that's going to be, once again, let's take the 360 and the sine of 25. And what I'm going to find from here is 360, 25 sine divided, and then we take 80 in the sine, multiply, and I get 838.9 pounds. So that's quite different from what I had over here. I must have done something wrong somewhere along the lines. So that's not good. Okay, so I was concerned by my answers not matching graphically, so I went ahead into AutoCAD, and I'm not suggesting that you would have to do this, but it is it is a solution. It is a method of trying to resolve when you get something that doesn't match, and I was able to confirm that. Well, actually, I think I got something. I wrote something down wrong. So it's sort of a little concerned here. Let's see. Did that not measure that thing correctly? Let me see here. My AutoCAD is sort of acting up. My computer overall is acting up. Let me see. I will go to this, and let me come to the very bottom here. Actually, let me zoom into there. Did that did come to one point, didn't it? Yeah. Let me actually go right into there. And here you go. Okay, yeah, 838. That's what I was expecting to get. 838.9. So yes, it confirmed what I got from the law of sines in there. So it was really just my pencil not being very good. I'm going to double check this for somehow. I don't understand how it could have been so bad in here. Especially since that my parallelogram seemed to match my, I see, so double checking in here. Here is my, what I said was 36, and I might have made that a little short, and I might have made that line not quite go to the tip. Oh, you can see down here, I've actually tried to draw this thing with a little bit more precision into there. Let's see, and bringing it down to there where they would have to match up right there. So I'm going to leave this here. It just, these are the values that I got. I'm not ashamed of the fact that I didn't get the correct answer by way here, but it's the process, not the, I did confirm that I did get the correct answer up there. So in answering my question, I see the question says we want to graphically determine the resultant force and force F2. So my resultant by way of graphically was approximately 730 pounds down. F2 was approximately 680 pounds. This direction at 65 degrees. When I did it graphically with a triangle, I found my resultant was approximately, and I think I got the same thing, right? 730 pounds down. And this time, though, because of pencil lead thickness, I get that to be somewhere, I say 700 pounds, right? And then when I do the law of sines and I do it trigonometrically, I find that I get a resultant of equaling 839 pounds straight down, and I get an F2 of approximately, not approximately, this is exactly, right? That's or as best I can there, 823 pounds, and I know that that's going to be the 65 degrees right there. All right, so there are my answers. I want to box them out. I'll make my box nice and neat. Very helpful to box out the answer. People will often just write a whole bunch of stuff and I can't find it. So there is problem, the first problem, and I will do the second problem here in a minute. And that took 24 minutes. So here's problem 2 of the homework, where we have now this cantilever beam, and it has forces F1 and F2 on it, and we want to find the resultant graphically using parallelograms and graphically using triangles, and then we can also find it trigonometrically. I can't pronounce that. Using log sines and log cosines. So here we go. Here is our paper, and we'll start out. This is going to be sheet 3 of our homework. Here's my name, Dr. Deal. And this is the spring of 2021. We're in ES110, and this is homework 1. Right? And this is problem 2, and I will make a brief sketch of what the thing looks like. Here is my wall, bop, 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 and here is my cantilever beam. And it's I'll put a little line for the flange, a line for the flange, and let's see. Here is horizontal sketched in. We have a force F2 that appears to be coming down this way. Let's see. They tell us that this is going to be 60 degrees. So this is like 30 degrees, something like that. I'll be more careful when I come up to the other side. So that's going to be F2, and here is theta 2, and maybe I'll make that line a little darker right here. Boom. And then here is going to be, let's see, this is theta 1 is 40 degrees right there, so something like this right here. Here's F1, and here's theta 1. And okay, so my given is that F1 is equal to 200 newtons, and theta 1 is 40 degrees, and F2 is equal to 300 newtons, and theta 2 is equal to 60 degrees. And for my find, I want to have find the resultant at B, right? Magnitude and direction, that's implied by this right here, and we want to do it A graphically with parallelograms. B graphically with triangles, and C using law of sines and law of cosines and law of sines, right? All right, so starting out right here, we have 200 and 300. So let me start with the F1, and I'm going to use plenty of paper here because why not? Right here. And there's the spot I'm going to start with, and I will take this and I'll measure it. And so that first one is 40, so that's this right here. Let's hope that we could do a better job graphically on this one than we did on problem 1, because that one graphically did not do us a lot of good. So I'm going to go ahead and stick with here. I'm going to go with 4 centimeters or 40 millimeters right there. There is my vector right here. And then this one right here is going to be 60 degrees, so I'll come back out over here and say here is 60 degrees right in there. And if somebody could try to figure out by looking at this, by watching the videos or looking at my thing, if I've made a mistake, maybe I should award bonus points for when people figure out what mistakes I made. So there's F1 and there's F2 right here, and so graphically right here, what I'm going to do is I'm going to move this guy over to here, right? And I'm glad I used enough space. I could have planned this a little better, but Maybe what I want to do is, how do I want to do that? Yeah, maybe I want to get, oh, did I measure how long the thing is? I don't think I did. That was silly. All right, so there's 300 right here, right? So there was, I went and made that, I accidentally made that twice, right? So I had to be careful here. So I went ahead and I did that to 40 right here as opposed to here. So let me double this. So that's going to be 6 right there, right? I didn't bother with, I was just talking and writing at the same time. So, it's hard to think and talk at the same time. And you'll notice that with many of your fellow human beings. I'll have that trouble. Okay, so right there is where we're going with this. Let me see. I will draw that over to here, and so I'm going to try to be just a little bit more careful because I got burned the last time, right? So right there to there should be our right. So if we were to do this correctly right here, I'm going to guess that it's right there, right? So is that going to be parallel? Yeah. So here is where we're predicting that the resultant is going to be. Right there. That's what I'm predicting my resultant will be. And that prediction says that we're going to have, it looks like, well, so we're coming out to right around, that looks like it's 68, but we have to divide it by 2, right? So 68, so that should be 34 or 340. So I'm going to say that my resultant prediction is about 340 pounds. And what is my angle going to be? Well, I want to do it from horizontal. So here is the horizontal right here. So we want to measure that angle right in there to be able to report it. And so we're predicting that it's coming down in that quadrant right here. And if I'm going to say it's from horizontal right here, I am going to predict this out. I got a hair that's like right on my nose right there. It's going to drive me nuts. That looks to me like it's 65 degrees, believe it or not. All right, so that's going to be 65 degrees. Okay. So let's go to a separate page here, and we'll write all this out. So this is going to be page 4. And Dr. Deal. And I don't know if this is going to work out through the whole semester. This could take a long time trying to make a video for every one of these problems right there, right? Homework 1, and this is problem 2, continued right here, especially if I start messing all these things up. Okay, so once again, I'm going to start somewhere right here, maybe. Right here's the spot I'm going to start. And this one, once again, oh yeah, I need to make this 40 degrees, right? So here's with vertical, and here is, let's see, start right there, 40 degrees, right? So I decided to use, multiply it by 2 right there. So there's 4. So that right there should be the vector that I get, right? And now I want to add onto this. So that's about where the length of that thing ended up. And now we want to go from, let's see, we have that angle right in there. So we want to draw that vector coming down this way. So which way do I want to go? I'm going to come up to here, right? And that angle is 60 degrees, so that should be, am I doing that right? 60 degrees, I think so. Yeah, so like right there. So I'm going to draw this into here. And then this length of this is, what did I say? 300. So that's going to make it 6 to right there. So the triangle should be end up right there, right? So this vector right there is going to be that. So this was F1 right here. Here's F2. So here's our resultant right in there. And so this goes nose to tail right here. So we should go this way right down here. And our resultant should be here. So, and based on this, it looks like I have maybe somewhere like 66 this time, right there. So my resultant, let's see, I'm putting that too far over to the side. I'm estimating that my resultant is approximately, so it's 66, so that should be 330, right here, 330. And these are newtons. I actually wrote on the previous page, I accidentally gave it the wrong units. Whoops. So those are newtons. Yeah. And then as far as an angle goes, let's see. I want to do it from horizontal. So looking at this from horizontal, and I've got to use this scale right in here. And if it extends, once again, that looks pretty close to 65. It looks to me like if I was going to be a little bit more careful on there, that's 66 degrees. Okay, so now we have the dangerous spot here. Let's write out what these angles are. That guy right there, no, okay, so first off, well, we were given that this is 40 degrees, so this one right here should be 50 degrees, right? It doesn't look quite like 50. I guess it's close to 50 degrees. This angle right in here was given to us as 60 degrees. Okay, right? So let's write that in there. So this angle right in here, right, should be 40 degrees. Is that true? Right here, 40 degrees? Because that's 50. This is a right triangle, so this should be 40 degrees. So if that's 60 and that's 40, this right here should be 180. So this angle right in here, which I'm going to call beta again, is I just like to use beta, is going to be 180 minus 60 minus 40. So this ends up being beta is 80 degrees. Okay. So now I use law of cosines because I have this magnitude right here, which is 200, right? 200 newtons. And I have this magnitude right here, which is 300 newtons. And from that, I can find what my magnitude is going to be. So the law of cosines, I'm writing out onto this, is going to be R is equal to the square root of 200 squared plus 300 squared minus 2 times 200, 300 times the cosine, is this opposite, that beta, of 80 degrees, right? And I'm going to find my R. It's going to be 200 squared, 300 squared, add them together, 200, 300 times each other times 2, and then the 80 cosine times that, subtract, take the square root, I get 330.4 newtons, which is pretty close to what I got graphically. Yay. And then I use the law of sines to find the other angles. I think the one that I want to try to get is this angle right in here, because then I can find that angle. So I'm going to call this one, I think that's a psi. And so let's see. I know this guy right here now. So I'll take the law of sines and I'll take 330.4 divided by the sine of 80. Set that equal to F2, right? So F2 is opposite from there. So F2 is 300. And take that the sine of, okay, that's the thing I'm trying to find. Duh. And if I do that right there, let's see, I will take that over to the side and I divide that out, right? So I take 300, multiply it by the sine of 80, boom, and then divide it by 330.4, and then I take the inverse sine of that, and I get it to be 63.41 degrees, and therefore the angle that I want is 180 minus 50. See, got minus 50 and then minus 63.41. So there's 50, add there, 180 minus, and I get 66.59 degrees. So my answer is that R is equal to 330.4 newtons at this angle right here of 66.59 degrees. So if I want to put down the answers to what I have here, I say here, oh, I want to put the estimate thing. All right, so this is for the parallelogram method. I found that we had 340 newtons at 65 degrees. B, I found that I had 330 newtons. I said it was 66 degrees here. And then lastly, R, and I'm going to set this equals because I believe I got it right. And I'm just going to use 3 sig figs, 330 newtons and 66.6 degrees. And then I will box this out here. And I could have done this in AutoCAD too, just to confirm, but I feel pretty good about my answer right here. And voila! Let's see, what was the total homework time that it took for me to do this? It was 43 minutes, 45 minutes. Okay. I didn't take any shortcuts. I think that's a pretty fair assignment. Hopefully this won't take you more than double the time, 2 hours to do. I think that's a reasonable thing. An hour and a half maybe should be probably all right. So thank you very much, and I hope this helps you.